Hello, my name is Guillaume Bach. This is a pre-recorded presentation for the 2021 meeting of the Society for Mathematical Psychology. Today, I'm going to talk about a simulation study on how personalization algorithms can guide or distort category learning. The use of personalization algorithms has become prevalent on the internet. We are already familiar with this type of service, providing recommendations for movies, music, foods, and so on. Even the researcher community benefits from personalized suggestions of recent research articles and researcher networks. However, the application of personalization has brought up discussions on its detrimental effects. A filter bubble is a good example. Simply saying, a filter bubble refers to the algorithmically curated presentation of homogeneous content to users. The problem brought up by filter bubbles is that we end up putting ourselves in the environment where our belief is reinforced, regardless of whether it is correct or not, by the information that is curated by external algorithms. As a result, personalization algorithms have been discussed as a major source of confirmatory bias and polarization on the internet. Previous studies on personalization algorithms have mostly focused on consumer behavior. However, a recent preprint provides us a different perspective. The authors conducted a systematic review of the effect of the YouTube recommender system. The main research question was whether the recommendation algorithm facilitates problematic content pathways. According to the authors, 21 out of 23 papers concluded that the algorithm obviously or possibly guides YouTube users to the problematic content. And the content discussed in the review paper suggests that many of them are related to factual and conceptual learning. The effect of personalization is not limited to consumer behavior, and this review implies that personalized content can affect our concept and knowledge structure. In this study, we aim to investigate the effect of personalization on category learning, which is strongly related to the development of concepts. Here, we used a cognitive model-based approach to specify the behavior of attention-based learners. Also, we developed an interactive architecture that simulates curated learning procedures. We will start from introducing the basic experimental setup. Let's say the goal of this experiment is to learn about animals. A creator finds an item that might interest the learning agent. Each item consists of multiple features, which can be represented as a multidimensional feature vector. For example, a cat is toothed, has legs, has fur, has a tail, and so on. However, the creator does not reveal all of them at once to the learning agent. For example, the learner first shows a feature, has fur. The learner is interested in this piece of information and decides to encode it. The learner updates one's memory by storing the present feature. The creator also recognizes that the learner encoded the presented feature from its response. The creator updates its knowledge about the learner's preference on encoding so that it can find another item that could interest the learner in the subsequent trials. Meanwhile, the creator shows another feature, has legs, to the learning agent. However, the learner is not that interested in this feature and decides not to encode it. With this decision, the learner wants to stop learning about this animal and move on to the next one. As the trial ended, the learner updates one's attention based on the encoded information. The creator also updates its knowledge about the learner's preference and prepares the next item. In this simulation experiment, we assume that a learner and a curator interact and exchange information, and we need to specify the model of learners and curators that enable this interactive learning process. A learner needs a model for representational learning that can store information. Also, to make dimension-wise encoding decisions, it must have a decision rule as well. A curator needs to learn the learner's preference based on the explicit encoding decisions and generate proposals for them. We will discuss the agent models and the basic architecture for the task from now. In this study, we used the adaptive attention representation model as a representational component of the learner's model. In this model, both memory on the category representation and dimension-wise attention adaptively change over trials. As selective attention is known to play a crucial role in category learning, the ability to realize trial-by-trial attentional dynamics is important in explaining the learning trajectory. Especially in this model, Attention distributed across feature dimensions is reallocated based on the computational principle of gradient-based optimization. This property makes the learner well-intentioned, which means that it always tries to make the best possible use of the collected information in adjusting one's attention. The model also pursues parsimony in attentional reallocation by introducing various simplicity-inducing biases. The details of this model are discussed in another MathSci talk this year, The Quest for Simplicity in Human Learning. We strongly recommend this presentation if you are interested in the model's mechanism. The learner stores the information and allocates attentional resources, but this is not everything. The learner must also make dimension-wise encoding decisions. We can take various approaches, but here we assume that the encoding probability for a certain dimension is determined by the logistic transformation of the associated attention weight. If a dimension is given a high attention weight, the dimension becomes more likely to be encoded by the learner. Now we will discuss the basic structure of the curator. A curator's goal is to maximize the chance that the learner continues consuming information, in other words, encoding as many features as possible. For this purpose, the curator has to learn a user's choice history, evaluate its preference, and generate appropriate proposals. We assume that the curator has access to the learner's encoding decisions, which are manifest variables. The curator records the dimension-wise encoding rate and uses it as a user's profile. This profile is renewed based on simple Bayesian updating. In particular, a learner's dimension-wise preference is modeled as a set of beta-distributed variables associated with Bernoulli decisions, encoding the dimension and not encoding the dimension. If a learner decides to encode a particular dimension, the curator updates the first parameter of the beta distribution, which reflects the encoding decision. If a learner decides not to encode the decision, the curator updates the second parameter, reflecting the dimension of not encoding. With the user's profile, the curator wants to select one item to be presented on the next trial. For this purpose, the curator evaluates the utility of each item in the dataset based on the user's profile. Here, the utility refers to the expected number of encoded features, which is connected to the curator's goal of maximizing information consumption. If the curator is interested in improving the quality of personalization, it can limit the number of candidates by selecting items with the highest expected number of encoded features. Then, based on the evaluated utility of each item, the curator chooses one of the candidates as a proposal for the next trial. Also, the curator can switch the presentation order of the item's features in descending order of the encoding rate. As the decision to not encode a feature will make the curator stop exploring the present item, showing the dimensions with the higher encoding rates first can guide the learner to encode the maximum number of features. Although I will not go through all the details due to time concerns, we have assumed two different counterfactual scenarios. The first one is a random learning sequence. Unlike the curation condition, where a curator guides one's learning in a particular direction, a random learning sequence has no such bias. Another scenario is active learning. Unlike the curation condition, where a curator has full control over the learning trajectory, the learner controls one's learning experiences in active learning conditions. In particular, for the dimension level search, we assume that an active learner explores the dimensions based on either one's internal attention weights or the predicted probability of category membership given the already sampled features in the previous steps. We tested two possible variants for each case. How can we evaluate the behavior of the simulated learners? In this simulation, we tested the model in environments with various underlying structural forms to see whether the conclusion can be generalized. Categories can be arbitrarily distributed clusters or can form a ring-shaped, ordered, or tree-like structure. More importantly, we tested the learner's knowledge with a separate set of items that have not been shown during the learning phase. Predictive accuracy and entropy are the measures of our interest. Especially, the predictive Shannon entropy is related to the confidence of the learner's prediction. First, we will compare how the attention weights change over trials across different conditions. The trial-by-trial attentional dynamics discussed here were obtained from the simulated learning trajectories of the adaptive attention representation model. We will focus on the control, item-level creation, and feature-level creation conditions. The left panel shows some examples of the learners who went through the control condition with randomly presented items and perfectly encoded features. Here, the simulated learner ends up assigning high attention weights to 3 out of 6 feature dimensions colored in red, purple, and gray. However, in the middle and right panels in which curated learners are illustrated, you can find that important dimensions sometimes fail to gain enough attention. In contrast, less important dimensions sometimes gain more attention. In particular, learners in the feature-based curation exaggerate the importance of a fewer number of dimensions. Next, we will discuss the predictive analyses. A series of box plots will be shown that compare the control condition, item-level manipulations, and feature-level manipulations. You can find the results of the curated learning conditions within the rectangular boundaries. The first set of box plots shows predictive accuracy. Across all 4 tested environments, we can see that curated learners show low predictive accuracy. The second set of box plots shows predictive entropy. Note that we interpret low predictive entropy as higher confidence about one's prediction. Across all 4 tested environments, curated learners show low predictive entropy, although the ring dataset reveals low entropy even in the control condition. Lastly, we want to show how one's latent representations about the test items change over trials. We map the test dataset onto the multidimensional scaling or MDS space developed during the learning phase. The top right panel shows the ground truth MDS representations. At the very early stage of the simulation, the MDS solutions of the test items do not match the ground truth in both conditions. However, after only a few more trials, the best performing active learning condition starts to adapt the latent representation. After 300 trials, the active learner's representations are very close to the ground truth, but the curated learner fails to develop the appropriate representations. Here's the summary of the simulation experiments. Curated learners tend to allocate attention in a suboptimal fashion. Also, curated learners tend to be overconfident about one's prediction after learning, especially considering their low predictive accuracy. Lastly, curation hinders the development of the appropriate latent representation of categories. Thank you very much for your attention. Please contact us if you have any questions.